Welcome everyone. Today we're going to be talking about Chapter 7, Section 2, which is the calculus with parametric curves. So if f and g are differentiable functions of t and x equals f of t and y equals g of t, then dy dx is equal to dy dt divided by dx dt as long as dx dt does not equal to 0. So let's see why this is the case. So if we assume that y is a function of x, we can use the chain rule. So then we would have d dt of y. So then by the chain rule, that would be dy dx times dx dt as we differentiate through our intermediate variables. So then that would give us dy dt is equal to dy dx times dx dt. Solving that equation for dy dx by dividing both sides by dx dt, we get that dy dx is equal to dy dt divided by dx dt, which is what our theorem states. Okay, so it's worth noting that the second derivative of y with respect to x does not equal, we just take the second derivative of the numerator and denominator. So why would it be this? So we have d2y dx squared is d dt dy dx divided by dx dt. Well, it's actually exactly the same thing that we did above. So if we have y prime is equal to dy dt over dx dt, which is the same thing as dy dx, if we go ahead and take the derivative again, so we have d dt of y prime, well, that's going to be dy prime dx times dx dt. So once again, that would give us dy prime dx is equal to dy prime dt divided by dx dt. But dy prime is just the second derivative. So then putting all of this together, we'd get d2y dx squared is equal to the derivative d dt of y prime, which is dy dx, divided by dx dt. So keep that in mind as we move forward. All right, let's go ahead and take a look at our first example. So if we look at example number 1, we're asked to do the following. A curve is defined by x equals t squared and y equals t squared minus 3t. We want to show the curve has two tangents at the point 3, 0. Find the points on the curve where the tangent is horizontal or vertical. Determine where the curve is concave up or concave down, and then D, sketch the curve. So the first thing we need to do for part A is we need to solve the system of equations where we have x is equal to 3 and y is equal to 0. So those are our given points that we have right here. X is 3 and y is 0. So putting that into each of these equations, we have x is equal to t squared, so 3 is equal to t squared, and in our second equation, we have 0 is equal to t cubed minus 3t. So we solve our first equation on the left by taking the square root, so the two possible values of t are plus or minus the square root of 3. And on the right-hand side, we factor out our common factor of t, leaving t squared minus 3. Then that gives us t equals 0, or t squared minus 3 equals 0, which then tells us that t squared equals 3. So we get once again that t equals plus or minus the square root of 3. So the curve is at the point 3, 0 for t values for t equals the negative square root of 3 and t equals the positive square root of 3. So notice, even though 0 is a solution to the second equation, the curve is not at the point 3, 0 at time t equals 0, because when t equals 0, the first equation is not true. Okay, so now B, find the points on the curve where the tangent line is horizontal or vertical. So for part B, the graph will have a horizontal tangent line when the change in y is equal to 0. So for the horizontal tangent, we need to solve dy dt is equal to 0. And for the vertical tangent, we need to solve dx dt is equal to 0. All right, so we take our derivative. Dy dt is going to be (3t squared minus 3). So we factor out our 3 and we get t squared minus 1 equals 0. Then we get 3 times t minus 1 times t plus 1 equals 0. So that's going to have our solutions t equals -1 or t is equal to 1. So our curve is going to have a horizontal tangent line at t equals 1 or t equals -1. So then, to find the corresponding points on the curve, we need to put them back into the original equation. So our original equation for x is t squared, and then we have t cubed minus 3t. So x equals 1 squared, and then y would be 1 cubed minus 3 times 1. So that gives us 1, and 1 take away 3 is -2. So at the point 1, -2. If we put in -1, we're going to have x equals -1 squared, which still gives us +1, and y equals -1 cubed minus 3 times -1, which is going to be -1 plus 3, which is equal to +2. So then we would also have a horizontal tangent at the point 1 and -2. So now going back to find our vertical tangent, we set dx dt equal to 0. So dx dt is going to equal, well, the derivative of t squared is 2t, and we set it equal to 0, giving us that t is equal to 0. So then to find that point, we plug t equals 0 in for x, which is just 0 squared, which is 0. and we plug t equals 0 into y, which is 0 cubed minus 3 times 0, which is 0 minus 0, which is still 0. So we have the horizontal or a vertical tangent line, pardon me, at the point 0, comma 0. All right, so part C says, determine where the curve is concave up or concave down. So to determine the concavity of the graph, we need to find the second derivative, dy dx. So for part C, let's start with finding the first derivative. So we have y equals t squared and y equals t cubed minus 3t. So we have dx dt is 2t, dy dt is 3t squared minus 3t. And from our theorem above, we have dy dx is dy dt divided by dx dt. So we have 3t squared minus 3 all over 2t, which is our first derivative. So then we can break this up a little bit if we wish to 3 over 2t minus 3 over 2 times 1 over t. So that's our dy dx. To find our second derivative, d2y dx squared, remember that that's d dt acting on dy dt divided by dx dt. So now we need to take the derivative of dy dx with respect to t. So the derivative of 3 halves t is just going to be 3 over 2. And then we have minus 3 over 2 times 1 over t. But remember, 1 over t is the same as t to the negative 1. So we bring the negative 1 down in front, making this a positive 3 over 2. And then the derivative, we're going to have t to the negative 2, which is going to become 1 over t squared, all divided by our dx dt is still 2t. So then if we wish, we can factor out that 3 over 2, and we get 1 plus 1 over t squared divided by 2t, which is a form of the correct answer. And if we really, really wish, we can clean that up by multiplying both the numerator and denominator by t squared. So cleaning up a little bit more, pulling the 2 out of the denominator and multiplying the top and the bottom by t squared, we end up with t squared plus 1 over t cubed. And we want to find out, well, where's our graph concave up and where's our graph concave down? So the numerator is always going to be positive, and the denominator is going to have the same sign as t because it is undefined when t equals to 0. So then we have our number line. So then if we check something to the left of 0 for t, we have a negative. So we're going to get a positive in the numerator times a negative in the denominator. So that's negative. And if we plug in something positive like 1, 1 squared is 1. So 2 in the top divided by 1 cubed in the bottom is 1 is positive. So then that tells us that our graph is going to be concave down over here. So concave down for t less than 0, and it's going to be concave up for t bigger than 0. All right. So lastly, we want to go ahead and sketch the curve. So we had a couple of points up here. So we know that we have a vertical tangent at the point 0, 0. We also know that we had a horizontal tangent at the point 1, negative 2, and the point 1, positive 2. Negative 2 and 1 positive 2, and we know we're going to have a horizontal tangent there. And we could find our y-intercepts by setting y equal to 0. So y was equal to t cubed minus 3t. So factoring out our t, we get t squared minus 3 equals 0. So then we have our intercepts are going to be at t equals 0 or t equals plus or minus the square root of 3. We've got 1 here, and if we plug in plus or minus the square root of 3 into x equals t squared, we get that x is equal to plus or minus the square root of 3 squared. And a negative times a negative is a positive, and a positive times a positive is a positive, so we get the square root of 3. So we're going to have some x-intercepts at 3, and our y value there is 0. So then if we pick a couple of sample points and do this, we get a graph that loops back around. It looks something like this, where we had our graph and its concavity looks something like this. All right, so let's verify that on our graphing device. So remember, to put our calculator in parametric mode, you press your mode key, and we go down here and change our calculator from function mode into parametric mode. And then we press our y equals, and we put our x and our y in. So our x is t squared, and our y is t cubed minus 3t. And let's go ahead and press our window. So let's change this to go from the negative square root of 3 to the positive square root of 3. And we press graph, and we get something that looks like this. So let's press window again, and let's just go from negative 2 to 2. See what this looks like. And we get a piece that looks like this if we go zoom. And we choose to zoom in by taking choice number 2. We get something that looks like this. And let's change our x-min to like 0.5 and make our x-max 4.5 or 4. And we get a piece that looks kind of like this, which looks similar to our rough sketch that we did by hand. All right, it's now your turn. So we've got a U try for you. So find the tangent to the cycloid t minus sine t and y equals 1 minus cosine t at the point t equals pi over 3, and find all of the points where the tangent line is horizontal. So to find the tangent of our cycloid at the point t equals pi over 3, we actually need to find that point. So we have x of pi over 3 is equal to pi over 3 minus the sine of pi over 3. That's pi over 3, and the sine of pi over 3, so sine pi over 3 is going to be root 3 over 2 minus root 3 over 2. And then we have y of pi over 3, which is going to be 1 minus the cosine of pi over 3. And the cosine of pi over 3 is going to be a half, so that's 1 minus a half, so we get a half. So then, if we wish, we can get a common denominator here. So we have 2 pi minus 3 square roots of 3 all over 6. So our ordered pair is 2 pi minus 3 root 3 over 6, comma, 1 half. So now we want to find the tangent to the cycloid at that point. So we need to know the derivative. So dy dx is going to be equal to dy dt divided by dx dt. So dy dt, the derivative of 1 is 0, and the derivative of negative cosine is positive sine t, divided by, and then the derivative of t minus sine t, the derivative of t is 1, the derivative of sine is cosine. And then we evaluate this at pi over 3. So dy dx evaluated at t equals pi over 3 is the sine of pi over 3 divided by 1 minus the cosine of pi over 3. So sine pi over 3 is still root 3 over 2. And the cosine of pi over 3 is 1 minus a half. So root 3 over 2 divided by a half, so we multiply by the reciprocal 2 over 1, and we get the square root of 3. So now we need the equation of a line that has slope square root of 3 and contains the point 2 pi minus 3 root 3 over 6 and 1 half. So we have y minus y1 is equal to m times x minus x1. So we get y minus a half is equal to the square root of 3 times x minus, and then we have 2 pi minus 3 square roots of 3 all over 6. And that gives us y minus a half is equal to the square root of 3 times x minus 2 square roots of 3 pi over 6, and then distributing in the square root of 3 and the negative sign, we're going to get a negative. Negative makes it positive. So I get 3, and then the square root of 3 times the square root of 3 is another 3 over 6. So now, finally, we get y minus a half is equal to square root of 3x. And we get a couple of things that reduce. So we get square root of 3 pi over 3, and then plus 3 over 2, and then we add a half, and we add a half, and we get y equals square root of 3x plus square root of 3 pi over 3, and 3 halves plus a half is 4 halves, which is 2. And that's going to be the equation of our tangent line. So now, the next thing we want to do is find out all points where the tangent line is horizontal. Well, we'll have a horizontal tangent line when dy dt is equal to 0. So dy dt, well, the derivative of 1 minus the cosine of t, so the derivative of one is 0, and the derivative of cosine is negative sign, so the negative makes it positive, so we get sine t. So then we set this equal to 0, and we have sine t is equal to 0. So solving, t is equal to the inverse sine of 0, which is 0. And then the period, the tangent function is 2 pi. And we know that sine is equal to 0 every pi units. So we have it 0 at 0 and it's 0 at pi, and then every 2 pi units thereafter. So at first glance, we may believe that that t is equal to n pi for n in the set of integers. So all of the multiples of pi. But we have to be a little bit careful. When we look back at our derivative, what was dy dx? So we had the following above. Dy dx is equal to the sine of t divided by 1 minus the cosine of t. So we have our derivative here, and we'll notice that at the odd multiples of pi, we have 1 minus cosine t is equal to 0 when cosine t is equal to 1. And when does cosine equal to 1? Well, cosine is equal to 1 at 0 and 2 pi and 4 pi and so forth. So we get that t is equal to the inverse cosine of 1. So in this set, we have t is equal to 0, 2 pi, 4 pi, and so forth. Well, if that's the case, then the derivative is going to be undefined at the even multiples of pi. So that will mean that we don't have horizontal tangents at those points. So we must reject any of these, so then we only end up having the horizontal tangents at the odd multiples of pi. So all right. So for our next thing we want to talk about is areas with parametric curves. So if a curve is given by a parametric equation, then the area underneath the curve from x equals a to b is the integral of y dx. So in order to use this definition, if our parametric functions are given as a parameter of t, we need to convert our limits of integration to two new numbers, alpha and beta, and integrate g of t f prime of t dt, where a and b, alpha and beta, are the solutions to the equations a equals x of t and b equals y of t. And g of t, y is equal to g of t, and x is equal to f of t. So find the area under one arch of the cycloid x equals r times theta minus sine theta, and y equals r times 1 minus cosine theta. Okay, so we need to find one arc of this. So that means we need to know when y equals 0 for the first time, and then when y, and we know that it starts at 0. So if we solve the equation y is equal to r times 1 minus cosine theta and set y equal to 0, we need to resolve 0 equals r times 1 minus cosine theta. So we divide by r, and that gives us 1 minus cosine theta is equal to 0. So just as we did above, we solved this equation for cosine theta. So cosine theta equals 1 implies theta equals the inverse cosine of 1. And that means we're going to have theta equals 0, 2 pi, 4 pi, 6 pi, ... forever. And we'd also have all of the negative ones as well. So it's really a plus or minus, plus or minus, plus or minus. So we need to find the area under one arc. So that's going to be the integral from 0 to 2 pi of y dx. So our y is r times 1 minus cosine theta times dx dt, and our dx dt is going to be, r is a constant, or in this case our dx d theta rather. We're going to have 1, and the derivative sign is cosine theta. So then we have r times 1 minus cosine theta d theta. So our r's are all constant with respect to this integral, so we pull the r squared out in front. And then we have 1 minus cosine theta times 1 minus cosine theta. We'll distribute that out, so that's 1 minus 2 cosine theta plus cosine squared theta d theta. And then, before we can integrate, we have to use an identity on this. So cosine squared theta is 1/2 times 1 plus the cosine of 2 theta. So expanding all of that out, we have r squared times the integral from 0 to 2 pi. So if we distribute that 1/2 in, we get 1/2 plus cosine 2 theta over 2. So 1/2 plus 1 is 3/2 minus 2 cosine theta plus the cosine 2 theta over 2 d theta. So now finally, taking the antiderivative, we get 3 over 2 theta. The antiderivative of cosine is sine, so still negative 2 sine theta. And then the antiderivative of cosine is still sine, but it's the antiderivative of cosine 2 theta. So using the chain rule backwards, and we have to divide by another factor of 2, which will give us sine 2 theta over 4. And then we need to evaluate that from 0 to 2 pi. if you want to, we can always let u equal 2 theta, then du is equal to 2 d theta, and do a u substitution on that, and you will end up with the same thing. All right, so now evaluating, we have r squared times 3 over 2 times 2 pi minus 2 times the sine of 2 pi and plus the sine, 2 times 2 pi is 4 pi over 4, minus, we're going to do some zeros, so 3 over 2 times 0, minus 2 times the sine of 0, plus the sine of 0 over 4. All of those terms being 0. Also, any multiple of pi for sine is 0. All of those are 0, 0, 0. So then in the very first one, the 2 and the 2 cancel, and we get 3 pi r squared for our final solution. All right, let's take a look at our next theorem. So we just did area. Our next theorem is for arc length. So if a curve C is described by the parametric equations x equals f of t and y equals g of t for alpha less than t less than beta, where f of t, f prime of t, and g prime of t are continuous on the closed set alpha beta, and C is traversed exactly once as t increases from alpha to beta, then the arc length is given by the integral from alpha to beta of the square root of dx dt squared plus dy dt squared dt. All right. So let's go ahead and use this to find our next example. So we wish to find the arc length of the following curve. So we have find the arc length of the unit circle x equals cosine t and y equals sine t for 0 less than t less than 2 pi. Well, we know what the answer to this should be. It should be 2 pi, because that's the circumference of a circle with a radius 1. But let's verify. So dx dt, the derivative of cosine is negative sine t. And dy dt, the derivative of sine is cosine t. So then we need to take the integral from 0 to 2 pi of the square root of negative sine of t squared plus cosine of t squared dt. Well, that gives us the integral from 0 to 2 pi of the square root of sine squared t plus cosine squared t, which is the Pythagorean identity. So that's going to be equal to 1. So now we just have the integral from 0 to 2 pi of 1 dt, or dt. So the antiderivative of dt is t, evaluated from 0 to 2 pi, is 2 pi minus 0, which is 2 pi. All right, it's now your turn. So go ahead and give this u try a shot. So it says find the arc length of the unit circle x equals cosine 2t and y equals sine 2t, and t ranges between 0 and 2 pi. So before we start, let's see if we can guess what the answer is going to be. So if we have cosine 2t and sine 2t, how is that going to affect our period of the sine and the cosine function. So normally our period is 2 pi, but if we have sine of 2t, we're going to be traveling around the circle twice as fast. So instead of wrapping around once, we're going to wrap around twice. So if we travel around the unit circle twice, instead of getting 2 pi, what should we end up with? Well, hopefully 4 pi. Well, let's see what we get. So we have our dx dt is equal to, the derivative of sine is cosine 2t, but then by the chain rule we multiply by 2. Similarly, we have dy dt is going to be the derivative of I was looking at the wrong one. Let's do that again. dx dt is x is cosine, so the derivative of cosine is negative sine. So we're going to have the sine of 2t, and it's negative, but then by the chain rule we should have gotten a 2. Similarly now, dy dt, the derivative of sine is cosine 2t. By the chain rule we get a 2 that comes out, so we get 2 times the cosine of 2t. So now we have the integral from 0 to 2 pi of the square root of negative 2 sine 2t squared plus 2 times the cosine of 2t squared dt. So negative 2 times negative 2 is positive 4. And positive 2 times positive 2 is also positive 4. So we get 4 sine squared 2t plus 4 cosine squared 2t dt. And if we factor out our 4 and use the Pythagorean identity, we have 4 times sine squared 2t plus cosine squared 2t. And sine squared plus cosine squared is still 1, so this is equal to 4. And then we have the integral from 0 to 2 pi of the square root of 4 dt, but the square root of 4 is 2. So that's 2 times the integral from 0 to 2 pi of dt. So we get 2t evaluated from 0 to 2 pi, which gives us 2 times 2 pi, which will be 4 pi, as we expected. All right, so let's look at our last example. So find the length of one arc of the cycloid, x equals r theta minus sine theta, and y equals r times 1 minus cosine theta. And our hint ninja shows up to let us know that we'll probably want to use this identity at some point. We used one related to it earlier when we were finding the area. So we want to find the arc length, so we need to know dx d theta and dy d theta. So dx d theta is going to be r times derivative of theta is 1, the derivative of sine is cosine, so minus cosine theta. And then dy d theta is going to be r, the derivative of 1 is 0, and the derivative of cosine is negative sine, so negative negative makes it positive sine theta. So there we're just going to get r sine theta. And here we get r times 1 minus cosine theta. So now, putting that into our formula, we have dx d theta squared plus dy d theta squared is going to be r squared times 1 minus cosine theta squared plus r squared times sine squared theta. So if we factor out our r squared and then expand 1 minus cosine theta, it's 1 minus 2 cosine theta plus cosine squared theta plus sine squared theta, then cosine squared theta plus sine squared theta is equal to 1. So then combining that with our 1 out in front, we get 2 minus 2 cosine theta, factoring out our common factor of 2, that's 2r squared times 1 minus cosine theta. So now we want to do this integral. So we knew earlier that one arch went from 0 to 2 pi, and then we have this, so we have what we just simplified, so 2r squared times 1 minus the cosine of theta d theta. So the 2 and the r squared are constant, so the square root of r squared is going to be r. So we have the square root of 2r times the integral from 0 to 2 pi, and then we have 1 minus the cosine of theta d theta. And so we're looking at this and we're like, dang, how do I do that integral? And then we remember the hint ninja showed up to tell us that something would be helpful. So we've got this identity, and we notice, well, we have a 1 minus cosine theta on the inside. Well, that's exactly what we have right here. So if I multiply both sides of this equation by 2, that says that 2 sine squared of, I'm going to put thetas in, is equal to 1 minus the cosine of 2 theta. Yeah, I'm jumping the gun. I'm going to put x's back in for a second. There we go. So now we have 2 sine squared x is equal to 1 minus the cosine of 2x. So we're looking at this, and we have this, and this is this. So then if that's going to be the case, what is our theta going to end up being? So if we have 2x is equal to theta, then x is going to be theta over 2. So then this guy is going to be this. So we replace our theta with theta over 2. So then doing so gives us the following identity. So if I plug this in here for each of these, I get 2 sine of theta over 2 is equal to 1 minus the cosine, and 2 times theta over 2 is just going to give me theta, but I'll write it out explicitly. So then these two guys reduce out. So finally, we get 1 minus the cosine of theta is equal to 2 times the sine of theta over 2, and I'm missing my square. So finally, we substitute this into our integral, and we have the square root of 2r, the integral from 0 to 2 pi of the square root of 2 sine squared theta over 2 d theta. So the square root of 2 comes out, multiplies the square root of 2 in the front, so we get 2r, integral from 0 to 2 pi, and the square root of sine squared theta is just going to be sine of theta over 2 d theta. And you might be saying, but whoa, hold on there, Professor Peterson. Isn't that the absolute value of sine theta over 2? Well, the period of sine theta over 2 is 4 pi, and it is positive from 0 to 2 pi. So we don't need the absolute values in this case. So now finally, we're ready to take the antiderivative, and the antiderivative of sine is negative cosine. So we get negative 2r cosine theta over 2, but then I have to divide that by 1/2. So we end up with negative 4r cosine theta over 2 evaluated from 0 to 2 pi. So then that gives us negative 4r times the cosine of 2 pi divided by 2 is just pi, minus a minus makes it plus 4r times the cosine of 0. The cosine of pi is negative 1, so we get 4r, and the cosine of 0 is 1, so we get another 4r. So at the end, we end up with 8r being the arc length of this. All right.